Thank you, everybody. Welcome to my presentation. My name is Intl Chen. I'm now a professor at the University of Winnipeg, Canada. The talk I'm going to present today is about an efficient algorithm to find the most popular package concerning a certain questionnaire. Here it is, the outline of my talk. First, the motivation of this work. For this, I show you what is most popular package concerning a certain questionnaire, why it is interesting, important, useful in practice. Then I shall show you a basic algorithm to solve the problem. Then I show you how this algorithm can be greatly improved by using the priority queue structure to control the tree searching process. Then I just show you our test results. Finally, I'll conclude the talk with a summary and a brief discussion on the future work. The motivation of this work is to find the most popular package according to a certain questionnaire or say query log, as shown by this example. By this example, I just assumed the travel agency wanted to know the favorite activities or say items of customers. As shown in this table, from this table we can see that the first customer wants to have activities such as hot spring and airline, but he does not want to have activity at glacier. But whether the activities such as riding, hiking, boating is available or not is not important for him. Then our goal is to find not just subset of activities which can match as many customers as possible. In fact, for this small query log, we can find a set of 3 activities: hot spring, hiking, and airline, which can satisfy a subset of 3 customers, Q1, Q3, and Q5, because it is a maximum subset of customers which can be satisfied by a set of activities. Then what we have found, in fact, is a most popular package. To find the most popular package for a certain question log, our basic algorithm works as follows. Let Q be a query log containing m queries, Q1 up to Qn. Then we'll use Qij to represent the value of the jth attribute in query Qi. Then starting from the first attribute value, we'll divide all queries in Q into 2 branches. For every query Qi, if Qij equal to 0, we'll put Qi into a left branch. If Qij is equal to 1, then we'll put it into the right branch. However, if Qj is equal to don't care, we'll put it in both left and the right branch, showing quite different behavior from a traditional signature tree construction. For the above simple query log, we'll generate a tree like this. Essentially, the root of the tree represents the whole query log. It contains 6 queries. Then, according to the first attribute, hot spring, we'll divide the whole query log into 2 subparts. The first part is put in the left child lot, while the second part is put in the right child lot. And any query stored in the left child is with the value, attribute value for hot spring equal to 0. Where any query in the right child lot is with attribute value for hot spring equal to 1. But if the attribute value for the hot spring equal to don't care, this query will be put in both left child and right child. We just repeat this process until all the attributes have been checked. Then we just check all the leaf lots and find a leaf lot which represent a maximum subset of queries among all these leaf lots. Then we just go along the corresponding path bottom up to find most popular package. This simple algorithm can be greatly improved by using a priority queue data structure to control the tree searching process. The key of every element in this priority queue is just the pair like this. Here, SV represents the subset of queries represented by node V. And L is just the level of node V. We say a key value, which is a pair like this, is larger than other key value, which is another pair like this. If one of these two conditions is satisfied. The first condition is the size of the subquery represented by node V is larger than the size of the subquery of queries represented by node V prime. Or these two values are equal, but L is larger than L prime. Around this data structure, we have defined 2 functions. The first function is extract marks. And this function will remove and return the last key value from the priority queue. The second condition is quite simple. We just insert a new node into the priority queue. Then, for our new algorithm, at each step, 2 operations will be performed. At the first operation, we'll find the largest key in the corresponding priority queue data structure. In the second operation, we just put all the children, the key values of the children of node V into the priority queue. Besides, the priority queue are used to speed up the tree searching process. Heuristic is used for choosing a next attribute A to generate the children of the currently encountered node. It is a set of two conditions. By the first condition, we just require that this value is maximized. The second condition is if more than one attributes satisfy condition 1, then we'll choose A from these attributes such that the number of queries in SV with the attribute value equal to don't care is minimized. Here we should notice that this notation is used to represent all those queries in SV with attribute A set to be 1. By this notation, we just represent all those queries in SV with attribute A set to 0. With these two mechanisms, we can design our algorithm to find the most popular package according to a certain questionnaire. Here, I just want to make a sample trees to show you how this algorithm works. At the very beginning, we'll generate the root of the tree. Then, the corresponding key value will be inserted in the priority queue. You can see it is a pair of two values. The first one is 6 because at the very beginning, the size of the whole query log contains 6 queries. This node is at level 0. Then when we take out this value from the corresponding priority queue, will generate the two children of this node. Then the key value of these two children will be put into the priority queue like this. Then in the next step, when we take the largest key value from the priority queue, will generate the children of the corresponding node. Again, the key values of these two children will be inserted into the priority queue once again, like this. In the next step, we'll take the largest key value from the corresponding priority queue, then the children of this node will be created. Then the key value of these two children will be inserted into the priority queue. We just continue this process until we meet two different nodes like this. Then we just try to figure out which one is with the largest subset of queries. Then we just go along the corresponding path, bottom up to find most popular package. Now, I would like to show you our experiment results. In our experiment, we have tested altogether 4 different methods. The first methods are described in our paper. The third one is based on the signature tree construction, but with different heuristics being used. The last one is just the approximation method. All these strategies are implemented by us in C++ language. All the test results can be divided into 2 groups. The first group is the test results on a real date. The second part is the test results on a synthetic data. The real date is just the query log containing 1 different questions produced by a Chinese restaurant over 10 different dishes. The synthetic data is a set of queries randomly generated in which the number of zeros, the number of ones, as well as of the number of don't cares are evenly populated. On this slide, I just show you the test result on the real date. From the first figure, we can see that, by the first 3 methods, we can find 14 satisfied queries from 100 queries in the query log. But by the approximation method, only 7 queries, satisfied queries can be found. But from these 2 figures, we can see that the approximation method has the best performance. But our method is not so worse than the approximation method. On this slide, I just show you the first test on the synthetic date with varying number of attributes. From the first figure, we can see that for the first 3 methods, the number of satisfied queries found by these 3 strategies are comparable, much better than the result obtained by the approximation method. But again, from these 2 figures, we can see that the performance of the approximation method is the best. But our method is not so worse than this approximation method. On this slide, I just show you the second test on the synthetic data with varying query log size. Again, from this figure, we can see that the method based on the priority queue has the best result, considering both the quality of package found and the performance of the algorithm. In summary, in this talk, we have presented an efficient algorithm to find most popular package according to a certain questionnaire. The main idea is to use a priority queue to control the tree searching process, and a heuristic for choosing an attribute for construct the children of the currently encountered lot. I have also shown you the test results, which show that the method based on the query queue is the best. Finally, as a future work, we are interested in seeking an approximation method, but with both high quality of package and high performance of the algorithm. Okay, that is all for this talk. Thank you for your attention.